Okay, so now we're going to get into a discussion of something a bit different. And you might not see the connection yet, but this is actually going to lead right into discussing how the electrons are actually arranged in atoms. So we need to understand before we get to that the nature of waves or wave motion, right? Now, what you see on the screen here is something that I'm quite sure we have done ourselves as kids. If you have a rope which is attached to something fixed, and then you simply vibrate the rope by using an up and down motion, you'll generate what is known as a wave, right? And the waveform basically transmits energy along the length of the rope. Of course, the wave is moving along the rope, but the rope particles are basically in the same location. In each case, they're just moving up and down. So if you just focus on one point of the rope, initially it will be moving up, then it will move down, and then, and then it will be moving up again and down and so on. And while that is happening for that one point of the rope, the waveform which is produced will be moving right down the length of the rope. All right. Now, this is, of course, something that we can see in person, but there are other phenomenon which can be described as a wave form. For example, electromagnetic radiation of all forms, including visible light, can be expressed as a wave motion. Sound can also be expressed as a wave motion. So the principles that are involved in this simple experiment right here can be applied to those two situations, can also be applied to a certain type of electric current. All right. So if we understand the principles here, then that would go a long way in terms of us understanding how electricity behaves, how sound waves behave, how electromagnetic radiation behaves. All right. Now, we're going to get into the different characteristics of all waveforms, right? And we're going to use the wave nature of light. As I said before, light or electromagnetic waves electromagnetic radiation can be expressed as a form of wave, right? So what you see here on the screen in this page is basically a diagram explaining electromagnetic radiation. Basically, it consists of two forms, as the name suggests. You have the electric field component and the magnetic field component, which are at mutual right angles to each other, right? So the red line here shows you the waveform for the electric field component, and this other line which is parallel to it, which is black here and blue here, and black here and blue here, that would be the magnetic field component, right? And all electromagnetic waveform basically exist as demonstrated here. So let's look at the characteristics associated with waveforms. And the first one we're going to talk about is the wavelength. And the wavelength, by definition, is the distance between any two identical points in consecutive cycles. In some textbooks, they simply define it as the distance between two successive peaks or the distance between two successive troughs, all right, of the wave. So the symbol that is used for wavelength is this Greek letter here. It looks like an upside down Y. It's actually a Greek letter known as lambda, all right? So that's one particular characteristic of any waveform, the wavelength, all right? The other characteristic is known as the frequency. And the frequency, by definition, is the number of cycles of the wave that passes through a point in a unit time. And it is represented very often by the Greek letter nu. It looks like a V here, but it's actually a Greek letter nu, N-U. However, in some textbooks, they still use F to represent the frequency. So I have no problem if you use F to do that. And then we have the third characteristic here known as the amplitude. And the amplitude of a wave is its height, the distance from the line of no disturbance through the center of the wave peak. So if I were to go back to this slide right here, and let me choose my writing function here, the amplitude of the wave here would be given by this distance, whoops, right, from here to the line of no disturbance here, right? So that's the amplitude. All right, whoops, that would be the amplitude, okay? So that's the amplitude of the wave, the distance between the peak and the line of no disturbance. All right, so those are the three main characteristics of a wave. And it turns out that there's a mathematical relationship between the wave length and the frequency of a wave. And it is given by this equation right here. The frequency multiplied by the wavelength would be equal to the speed of the wave, all right? Nu times lambda is equal to the speed of the wave. Now, it turns out that all waveforms, all electromagnetic radiation moves at the speed of 3.00 times 10 to the 8 meters per second. That is true for all different waveforms or radiation waves, which include light. The light that we observe, we can see the different colors of light. They all travel at the same speed in a vacuum. And this page here, let me go back to this page right here, gives you the full, what we call the electromagnetic spectrum, which gives you the full list of the different forms of radiation. Now, in this particular version that you have here on the screen, they're arranged in order of decreasing frequencies going from left to right, which means that going from right to left, the wavelength would increase because, as we said before, and let me write this down here just to remind you, that the frequency of the wave, whoops, times the wavelength would be equal to the speed of the electromagnetic radiation, which is a constant at 3.00 times 10 to the 8 meters per second, right? So because this is constant, right, that means that there's an inverse relationship between the frequency and the wavelength. So as the frequency increases going from right to left, the wavelength would decrease and vice versa, all right? So to the extreme left here, high frequency, those are the gamma rays, right? And then next would be X-rays, which would be less. And then here we have what is called the ultraviolet region. And then you have a narrow band right here, which basically represents where you'd find the different colors of light. So as you can see there, it starts off with red. Let's start from this end here. Red running into orange, running into yellow, then green, then blue, and then indigo and violet. I cannot tell the difference between indigo and violet, but you know, I accept the fact that those are two different colors very close to each other in this region right here. All right, and then beyond that now you have the infrared region, and then you have the microwave and the different forms of radio waves, including FM radio, AM radio, cellular phones, frequencies, and so on. And then down here you have the extra low frequency radiation, AC current radiation, and so on. So that's basically the full extent of the electromagnetic spectrum. They all have the same speed, but of course the frequency and the wavelengths will be different. All right, so okay, so that is that. Now, let's talk about what is known as the continuous spectrum, which is that narrow band of the electromagnetic spectrum that we talked about. We can actually produce that if we have this kind of setup here. So what we have here is the light source, which produces light, which is converted into a beam using this slit right here. And then it hits upon this prism here. This prism can be made out of plastic or glass. And what happens as the light passes through the prism is that it undergoes what we call refraction, which basically means that the light bends as it passes through the prism. And what you'll find is that the different forms of light will experience different levels of refraction, and that is the basis for the separation of the white light into the different colors right here. And then when it emerges from the prism and projected onto a screen, you end up with what is known as a continuous spectrum, right? And it's, of course, it's called continuous because as you go from one end to the next, there's no line of demarcation between the different colors. So you'll notice that the red runs into the orange, which runs into the yellow, which runs into the green, which runs into the blue, which runs into the indigo, and then violet. All right. Oh, by the way, and I probably should have mentioned this before, there is a mnemonic that I use to remember the order of the colors. It is known as Roig-Biv. Let me just write it down here. Roig-Biv, right? That gives you the order of the different colors in this part of the spectrum, the visible part. Red, orange, yellow, green, blue, indigo, violet, all right? Okay, so that's the continuous spectrum. Now, let's say some more about the continuous spectrum. So what we see here are the different wavelengths of the different colors of light. So in the red region, the wavelength is approximately 650 nanometers. In the orange region, it's about 575. And you see the different values given for the others, all right? So basically the wavelength increases going from the indigo or violet region up to the red region. And of course, based on the wavelengths, you can calculate the frequency, because remember we said, let me do it down here, that the speed is equal to lambda times nu. So if you want to find nu, that will be equal to c over lambda, right? So if you want to find the frequency of the red colored light, which is approximately 650, we take the 3.00 times 10 to the 8 meters per second, which is always going to be the speed of light, divided by the wavelength, which is 650 nanometers. But we have to convert that to meters. So we have 1 nanometer down here, 10 to the minus 9 meters above. And then we do that calculation. So let me do that here. 3 times 10 to the 8 divided by 650 times 10 to the minus 9. Oh, let me do this again. I'm sorry. 3 times 10 to the 8 divided by 650 times 10 to the minus 9. And according to my calculations, the answer here turns out to be equal to 4.6, well, let's round it up to 266 times 10 to the 14. And the units here would be meters, because, I'm sorry, not meters, seconds to the minus 1, all right? And the reason why that is so is because the nanometer units will cancel out here and here, the meters will cancel out here and here. Now, one thing I should say here is that the second to minus 1 units is also known as the Hertz unit. So we can write this down as 4.6 times 10 to the 14 Hertz, right? This is a symbol for Hertz, Hz. Hz, let me write it up here. Hz is the same thing as the Hertz unit, which is the same thing as seconds to the minus 1, which is the same thing as 1 over seconds. So that's the Hertz unit, which is a unit that is used for frequency. As far as wavelength is concerned, the wavelength can be expressed in pretty much any metric unit, nanometer, meters, etc. But for frequency, it is always expressed in Hertz or seconds to the minus 1. Okay, continuing. So now that we have understood the whole concept of the continuous spectrum, let's look at another phenomenon which is kind of related, known as the line spectrum or line spectra. Now, what you see here on the screen is a setup where we have a gas, in this case hydrogen, trapped in a tube, and it is connected to 2 electrodes. You have 2 electrodes in there, which is connected to an external circuit. And then when the circuit is switched on, what was discovered was that the hydrogen starts to glow with this kind of pinkish color. All right. And if you were to project that light onto a prism as we did before, and then project it onto a screen, what you'll end up with is not a continuous spectrum that we observed before when we used white light. We end up with what is known as a line spectrum, which basically consists of lines of different color, indicating that the hydrogen is producing not the full spectrum of visible light, but different lights of different frequencies or wavelengths. So I don't know if you can see it here. Here's a kind of reddish pink line right here, and there's a blue line right here, and then you have, I guess this is indigo and this is violet. All right, so that is what happens in the case of hydrogen. It produces this particular spectrum. And what was discovered subsequently was that if you set up the same experiment using different elements but the same conditions, it's a gas under very low pressure. I should have added that. The pressure of the hydrogen is very low, and you subject it to an electric discharge, then what you'll find is that light will be produced, which would form what is known as a line spectrum. So you'll notice that the difference between the line spectrum and the continuous spectrum is that you have huge dark regions here in between the different lines, right? In the case of the line spectrum. In the case of the continuous spectrum, you have the colors running into each other. Okay, so what does this tell us about the nature of the elements? Well, before we get to that, I just want to show you this here. This is basically showing you the line spectra of different elements. And we can actually use the line spectra to identify elements, because each element has their own unique line spectrum. And in fact, this is what is used to determine what elements are present in the stars, such as our sun, right? Astronomers have instruments that allow them to look at the radiation coming from the sun, for example. And based on the line spectrum that they observe, they can identify that certain elements are present up there in the sun, all right? Okay, so another term for line spectrum, we call it the atomic emission spectrum, and we're going to see the reason why this terminology, emission, is important when it comes to describing this phenomenon. Okay, so let me stop this video here, and then we'll get into a discussion of the quantum theory as it relates to black body radiation.